maybe this could be called consider a circular landscape. I'm going to talk about a theory of macroecology, which means a theory of the distribution and abundance of species across spatial scales. And a sub-theme in what I discuss will be what role is played by explicit mechanisms in ecology. And what I'm going to argue is that if we start with an ultra-simple theory, lacking mechanism, and pursue its predictions and compare them with real data by looking at the deviations between very simple theory and the real world, we can begin to back out of that pattern of deviation which mechanisms are important. So I'm not anti-mechanism, but I find when I look around at all the wealth of potential mechanisms that people talk about in ecology, that there are so many, they are very complicated, there are multiple ways of describing them, and trying to start building theory with mechanism in it seems to me personally to be a virtually hopeless exercise. And so I want to start without mechanism, and then when I'm forced kicking and screaming into accepting mechanism, I will do so. And I will give you one example of where I've had to do that here. So the goal of this work and this talk is to describe theory that realistically predicts patterns in the distribution of individuals within species across space and of species within communities, and to do this at multiple scales. Some very specific issues that we'll get to are how many different macroecological metrics can we predict accurately with how few input parameters. And what I will actually be developing and show you is that aside from a couple of explicit measured variables, which we call the state variables of the system, there are no adjustable parameters in this theory. So I have no knobs to twiddle to try to do fitting. This is not going to be an exercise in fitting of models with parameters to data. And then the second specific issue is, can we deduce from patterns and from mismatches between theory and data some information that's useful about which mechanisms actually matter? And I'm going to be presenting at the core of this theory a method from that originally came from the work of Josiah Willard Gibbs in a different context developed by Claude Shannon, who developed information theory. And then the Gibbs and the Shannon avenues of research converged in the work of Edwin Janes, two of whose important papers are listed here if you want citations. What Janes did was to look at an entropy law, not the classical one you learned in freshman physics that for closed systems, the change in entropy, which is heat flow divided by temperature, is either equal or greater than zero, the second law of thermodynamics. What Janes was looking at was something that is more general. If you have a probability distribution, P of n, and all you know about it is certain constraints, you might know some of its moments, for example, then you ask, what's the most plausible, least biased inference as to the shape of that probability distribution? And what Janes proved, mathematically, rigorously, is that if you know certain constraints on P of n, like some moments, and you maximize this quantity, which Shannon called information entropy, namely the negative of the sum over the variable n, P of n log P of n, you maximize it subject to the constraints, you get the best inference as to the shape of P. And if P is an energy distribution, then out comes the Boltzmann energy distribution from thermodynamics. In fact, from this starting point, out comes all of classical thermodynamics. When you maximize subject to a constraint, there's a Lagrange multiplier, for those of you who know the math, and the inverse of that Lagrange multiplier is kT, Boltzmann's constant times temperature. That's thermodynamics. But the theory is more general, and P can be anything, and this can still work. So we have a simple procedure that generates all of thermodynamics, no mechanisms. Contrary to what some people think, thermodynamics, statistical mechanics, is not a mechanistic theory of large numbers of objects. It's a result that comes from fundamentally from an information perspective. There's a third entropy law that I'm going to come back to at the very end of the talk and just touch on some speculatively, and that's the principle of maximum entropy production, different from maximizing entropy subject to constraints. This has to do with the rate of production of entropy. This just has to do with entropy itself. And we'll come back to point number 3 later. So just to repeat, the maximum entropy method of Jaynes, Shannon, Gibbs is we wish to infer the shape of a probability distribution, and let's say we know a set of constraints of this form, where the mean values of the f's, little f's, are equal to the capital F's. And we know the capital F's. Then if we maximize S subject to those constraints, we get the best inference. Let me say a word about the epistemology of all this, because it is confusing and it is new for some of you, I'm sure. Jaynes and Shannon emphasize that MaxEnt isn't science. Not rocket science, it's not science. It's actually what Jaynes called a cornerstone of the logic of knowledge. It's more general than science in a sense. Jaynes formally proved that the P of n that maximizes S is the least biased estimate of P, and what that really means is that the MaxEnt solution to P is the smoothest possible distribution that satisfies the constraints. When you maximize minus P log P, you're getting the smoothest distribution that maximizes the constraints. So least biased of above means that it doesn't assume anything that we have no reason to assume. If you use this procedure and you're ignoring some constraints that should be there, that you just forgot about, you may not get the right answer. And so this does not guarantee you success. What it guarantees you is that you're getting the least biased distribution subject to the constraints. So let's see what we can learn about macroecological phenomena specifying certain constraints at the outset, constraints that nobody could possibly argue with. And what we're going to try to do is derive a whole lot of different macroecological metrics. The species abundance distribution, the distribution of metabolic energy consumptions over individuals, the species area relationship, the spatial abundance distributions of the species. I'll explain all these in more detail when we get to them. And something called the energy equivalence rule that you probably heard about when you went to Brian Enquist's talk in the recent past. And the only input to our derivation of all these metrics, quantitative derivations, is that we're going to specify 4 state variables. So picture, let's say, the 50-hectare Barrow, Colorado Island forest plot, where we have on 50 hectares something on the order of 230,000 individual trees, greater than 1 centimeter in diameter, about 300 species of trees in that data set. So we have A naught, 50 hectares, S naught, total number of species for the trees, around 300, N naught, the total number of individuals in that area, so that'd be around 230,000 for that plot, and then something that we don't always have a good estimate for, but it will turn out not to matter, but we still need it in the theory. So we're going to have a variable, a state variable in the theory, which, because we don't know its value so well, is a bit harder to test. I'll show you how we can get approximate tests of the theory involving this. Basically, not knowing this The one thing we can't do is that second item, the metabolic energy distribution. But we can still get all the other predictions out of the theory. So I want you to consider with me now a probability distribution. It's a joint distribution in the sense that it's a function of two variables, N for abundance and E for energy, and it's subject to the constraints of the values of those four state variables. It's a little bit like thermodynamics, where the state variables might be P and V, pressure and volume, and number of moles of whatever it is in the system. These are the equivalent in this theory of those state variables in thermodynamics. And what is this distribution R? Well, R times dE, a differential element of energy, is the probability that if a species is picked at random from the species pool in A0, if you pick one of those S0 species, then it's the probability that that species you've selected has abundance N, and if an individual is picked at random from that species, then its metabolic energy requirement is in the interval E plus dE. So that's the what R is, and it satisfies three constraints. Three constraints. It satisfies a normalization condition. Any probability distribution has to do that. We're treating E as a continuous variable and N as a discrete variable. The average over little n is going to be the mean abundance per species. So it's the ratio of two of our state variables, N0 over S0. And if I look at the mean of N times E, from the way R is defined, this becomes the average metabolic energy requirement per species. So those are the three constraints. Those are the only ratios you can form from N0, S0, E0 that are independent. Later we'll come to where A0 comes in. That will be relevant to a second probability distribution we'll get to soon. Now, I'm not going to do the mathematics of the MaxEnt machinery. You have to take my word that if you run through all the mathematics that James derived in his papers, you will get this function for the probability distribution R. And from here on, I'm going to leave out the conditional probability and the state variables to just save space. So R of N and E is a product of exponentials divided by something called Z, which in thermodynamics you'll recognize as the thing called the partition function. And Z is a function of two Lagrange multipliers because R is a function of two variables, and we have two constraints. The constraints being the N0 over S0 and the E0 over S0. And so Z is the sum integral of this product of exponentials. And by definition, this then satisfies the normalization condition. Now, from that distribution, we can start deriving some others as well. You'll see as we progress that we're going to derive from all of this species area curves and many, many other things. But let's start with a simple one, namely the species abundance distribution. This is the distribution of abundances across species. So let's say I have a system with 30 species, and some of them have a single individual, some of them might have two. One of those species might have 4,000 individuals. So there's a probability distribution which tells us what fraction of the species are expected to have n individuals. That's the species abundance distribution, and I obtain it exactly by just integrating out the energy part of the R of E and N function. And so this is my predicted species abundance distribution, and we can compare that directly with data. Similarly, if we get rid of the n variable by summing over n, and if you go back to the definition of R, you'll see you have to multiply by S over n, then we get psi of E, which is the distribution of metabolic energies across all the individuals in the system. So those are two predictions. And let's look at the predicted species abundance distribution. When you integrate out E, you get the famous Fisher log series distribution. first derived over half a century ago. Posited, derived, all came from all different approaches. I wouldn't say derived from anything fundamental. Here it comes out of something I think is pretty fundamental, the MaxEnt machinery. This lambda 1 is the Lagrange multiplier, and almost exactly it satisfies this equation. There are corrections to this equation. You can solve it exactly in the sense that you can solve it numerically, but there's no analytic expression for lambda as a function of s's and n's. So you have to work with a transcendental equation here. Lambda 1 is just Fisher's alpha. For those of you familiar with Fisher's alpha, or Michael Rosenzweig's book, it's Fisher's alpha divided by n naught. Lambda 1 also, interestingly, is related to a parameter in the Hubble neutral theory. Lambda 1 is 1 minus the ratio of his birth rate to his death rate. So, and those are exact results. Let's look at the theory. I've tested this abundance distribution against I think about a dozen systems now, a dozen data sets for different habitats. I'm showing you 3 vegetation census data sets, and I'm only picking these 3 not because they gave the best fits, but because they typify the behavior of this function for different values of lambda 1. We have a 64 square meter serpentine grassland data set, which one of my former graduate students, Jessica Green, and I set up in 1998, which we measured the point locations of every individual plant. We had 37,000 and some individuals divided over 24 species. We go back and we recensus that each year, so we've got data over time. And I'm just showing you 1 year's data for the species abundance distribution. And this is a plot of log of abundance versus the rank order of the species. So the highest ranked species has the highest abundance, and its logarithm is about 9.5, the log of its abundance. The highest ranked species have the lowest abundance. Those are singletons with 1 individual, so they have a log of 0. There happen to be 2 of them. And with no adjustable parameters, this is the prediction. It turns out that for this system, S naught over N naught is very, very small compared to these other systems. And when S naught over N naught is small, lambda is small, and so this exponent is essentially 1, because lambda 1 is so small. Now, when you look at the Coccoli, Lucchio, BCI, San Emilio, and many, many other data sets, you find that this was an extreme, and the others have larger ratios of S to N. And therefore, you get a lambda term that's detectable, and it's a little hard to see the curve amidst a glob of data, but the curve that's predicted is going right up through the empirical data. So the theory is working well. We've looked at predictions of breeding birds in England, fish in a Venezuela river, loads of other vegetation censuses, and we don't see any serious mismatches between what this predicts and observed abundance distributions. We also get the energy distribution by summing over n, and turns out you get a more complicated function. Here it is. Now this involves both Lagrange multipliers, lambda 1, which I showed you, and lambda 2, which is simple. It's just the ratio of S naught over E naught. And this is not a reliable test. Here's why. This refers to metabolic energy, but nobody measures metabolic energy in 50-hectare plots. What you measure is, let's say, basal tree diameter, basal area. And then you have to use allometry to scale up to the mass of a tree, and then you have to use Bryan-Inquist's mass to the 3/4 to get you to energy. And there's a lot of room for slop in that progression. So taking the allometry to be as simple as can be, the 8/3 Powerlaw scaling between diameter and mass, and taking the three-quarter law to be exact, then the data and the theory are reasonably in good agreement. I don't take this too seriously because I don't really believe those allometries, and there is empirically a lot of scatter around the three-quarter law. The Enquist-West-Brown stuff gets you the right central tendencies, but it certainly misses the individual species.
Just clarify on that last slide, the horizontal axis is epsilon.
The horizontal axis is rank. So I've converted this into a cumulative distribution, and the cumulative distribution into a rank abundance distribution.
Of what?
Of, in this case, basal area against rank. So I converted energy to basal area, and then I took the empirical basal areas and plotted them against rank. Log of area against rank.
You have one plot. So what you're doing is you're saying the distribution of energies among individuals.
Yes. Oh, I see what you're asking. Yeah, that's right. That's exactly right. We can also determine a conditional probability, which we can call theta of epsilon or energy given n. And it's equal to the joint probability function R divided by the abundance distribution. This is the conditional probability that if an individual is selected from a species with known abundance n, then its energy requirement is in the interval E plus DE. And this is what theta comes out to be. It's just a Boltzmann distribution in n times E. And now if we multiply that by E and integrate over E, we get the total energy requirement of a species with abundance n. And you can easily see this is independent of n. That's what Enquist told you last week was the energy equivalence rule, for which there's empirical support. He goes further and then says if metabolic energy scale is mass to the 3/4, we get the Demuth rule, which says that abundance of a species scales as its inverse mass to the 3/4. So you take the mass of a typical adult, raise it to the minus 3/4 power, and that should be proportional to abundance. So a lot of things in ecology are coming out of this theory, the energy equivalence rule, for example, but we can't derive the Demuth rule unless we assume the metabolic law of Brown, West, and Enquist. Now, I want to consider another, and this will be the only other probability distribution you're going to have to contend with here. Another distribution, we're going to call it capital P, superscript A for area, subscript A for area, superscript N naught for the abundance of the species, and N is the variable. Here's what it is. We have a area, A naught, and within it, let's pick a cell of area A. Arbitrary, just located anywhere you like. On average, in a cell of area A, what's the probability that if the total abundance of the species in A naught is N naught, what's the probability that there are N individuals in that little cell? And that function we're calling P A super N naught of N. And under MaxEnt, we can work out what it should look like. Here's the constraint. The average over that distribution of N is just N naught times A over A naught. Has to be. And from that constraint and the MaxEnt machinery, we get a simple function for P, complicated equation for the Lagrange multiplier. We're calling the Lagrange multiplier lambda sub P, and it's a function both of spatial scale and N naught, and here's the equation that determines it. Generally, for most cases, this simplifies considerably, but this is the exact solution. And from this, we know the spatial distribution. We can test those spatial distributions, and we did this using likelihood methods for 782 plant species from all the Smithsonian forest sites, Enquist's San Emilio site, the Serpentine site up in California, And with those 782 species, we compared the predicted spatial distributions at two spatial scales, namely grid cells that for which there were 16 by 16 in the whole plot, or 8 by 8 in the whole plot. And the maximum entropy prediction is right here, and these likelihood functions have these are actually root mean square error functions, so they're sort of the inverse of a likelihood, have a minimum at the value of a parameter, which we're just calling the aggregation parameter, 1. We've set up the parameter so that 1 is the value at MaxEnt, and you can see that it's a shallow minimum, but it's nevertheless a minimum at that particular aggregation parameter. Just to show you a couple of specific species and how MaxEnt compares with other theories, these are from the BCI, Barrow Colorado Island data set, and a species whose total abundance was 3,144 individuals, and another one was 638. These are at spatial scales where the little area we're looking at is 1/256th of the total area. And the solid line is the MaxEnt prediction. The dots are the data. This happens to be what the Coleman random placement model would give. And this is what an earlier theory of ours gave, a theory called the heap model, which was published in Ecological Monographs a couple of years ago. Some of you I know have seen it. And the problem with heap was when you got to very high abundances like this, it started to fail. And MaxEnt corrects that failure, but it turns out in another limit it agrees exactly with the old theory, in a limit, fortunately, where the old theory worked well. So we are happy about this replacement of a falsified theory with a better one. This is the same kind of thing, but for another species. We can now derive the species area relationship. And if we know the species abundance distribution, which we do from MaxEnt, that's the Fisher log series. And if we know P, the spatial distribution for each species with abundance and naught, if I take 1 minus P of 0, I have 1 minus the probability of absence, which is the probability of presence. So if I multiply the probability of presence for an individual with the species with n naught individuals and multiply it by the probability of n naught individuals, sum over all n naught and multiply by s naught, I get the species area relationship. So area comes in as a subscript on P, and it enters specifically because the Lagrange multiplier for P depends on area. So here are 3 tests. And again, we've looked at tests for BCI and many, many other, this shows you BCI, but we've looked at all the Smithsonian plots. They all work well. Here are 3. For BCI, MaxEnt is the solid squares, the observed data are the open circles, and we capture the curvature of this is a log-log plot, log of species richness versus log of census plot area. And the theory captures the data, or the data captures the theory very, very well. Yeah. No? Okay. San Emilio, this is a site in Costa Rica that Enquest set up, and again, we capture the pattern of the species area relationship very nicely. Serpentine Site is an interesting story. First of all, these are clearly very curved. If you fit a straight line to the serpentine data, you get a straight line fit on a log-log plot, which means a Powerlaw relationship. The slope turns out to be about 0.21. You get a Powerlaw fit with an R squared of 0.9994. It's hard to get better fits than that. Now, granted, there's only 9 data points. So,
John, could you say again how P sub A changes with A?
Well, I mean, I don't mean to be facetious, but that's how. That's how. X is e to the minus lambda P. Here's X. And here's A.
Okay, so I guess
yeah.
Given that, how different is this from a simple Poisson prediction?
Well, you saw, because the Poisson prediction is this.
Is
or
that
this.
guy.
That's the Poisson model.
Okay, but in terms of A, when you plot this against A, as opposed to abundance.
Oh, then things get really weird.
Which is your next
very different. Because this is always decaying. This MaxEnt prediction must monotonically decrease. And if you plot the Poisson against A, as you get to a scale that's coarser than the abundance itself, so that A naught over A is greater than N naught, then all of a sudden this becomes monotonically decreasing. So you get a very different dependence on A depending on whether you cross the A over A naught less than or greater than 1 over N naught.
Okay, but in your next slide where you've got this plot against area, it would seem that since you know A and you know N, it would be hard not to get this right.
Oh boy, I can show you
I would be
many here. For example, a long time ago we worked on a fractal model. And aside from the fact that the math was fun, it was kind of a waste of time. But the fractal model would give everything is Powerlaw. Everything isn't Powerlaw. Some things get very close to Powerlaw, and the question will be why, and I'll show you why in a minute.
Okay.
But not everything is Powerlaw. And there are all kinds of theories that have poorly predicted species-area relationships based on this kind of formula. And if I put in the Coleman result for P, that Coleman means random placement, and I put in anything for phi, log normal, Fisher log series, whatever, I'm going to get not a power law, which would mispredict this, but something with way more curvature than the data or MaxEnt. So you can either get it wrong by having too straight a prediction or get it wrong by having much too curving a prediction. So,
but you have to approach density times area as an asymptote.
Yeah, no, in fact everything is pegged as slash data point.
It's got to be very close to that even when you're quite a bit below that.
Let me show you some predictions in a minute. I may get to it. In fact, right here. Let's look in detail at the tropical forest species area relationships. So here are the data, these circles. Here's the MaxEnt prediction, the straight lines. And these are two other theories. One is the Gleason logarithmic model, which you can't see it, but this is actually plummeting down to here, this curve. Somehow it didn't show up, but it's very negative. It misses these data by a long shot, and it misses these somewhat, but up here. The Gleason model misses the data by a fair amount. And then this is the Lomolino function, which was proposed by Rosenzweig and others, and there's some models that generate Lomolino functions, but it's not doing as well. I mean, it really isn't capturing it. And I know of no other theory that does as well on this data as this does. This is the same thing for the Santa Emilia data set.
Okay, I'm not an ecologist, so I don't have sensitivity to these numbers that you're showing. And what kind of error bar would one expect on those observations? What is the
it's a good question. The way these data points are collected is you look at every cell of a given area. Let's say we have a 64 square meter plot, and I look at every one of those 64 square meters, and I ask how many species are there. And I look at that across all 64 square meters, so I get 64 numbers. What I'm plotting is the average of those numbers. The standard deviation of those numbers is typically on the order of about plus or minus one species. It will be more at, it depends a little bit on scale, but it's on the order of it's on the order of 10%. On a log scale, it falls well outside these other predictions. Now, I didn't mention, but I need to, that there is a problem here. There's a slope discrepancy between the MaxEnt prediction and the data. And you could ignore that, but we didn't. We said, let's take that seriously, see if we can understand what's going on. So here I want to show you, here's a blow-up where you can see the detail better of the mismatch. Here's the MaxEnt data. The dashed line is just a Powerlaw fit to the data. And this is the MaxEnt prediction. And now, when we saw this, we scratched our heads and said, what's going on? Well, one of the things, there wasn't any such mismatch in the BCI plot, but there's a property of the Serpentine plot that I haven't mentioned to you yet, so I will now. One quadrant of that plot is practically all barren. It's rocky outcrop. There's about a fifth or sixth as many individuals in that quadrant as in the other three quadrants. So we said maybe that's a problem. So we took the quadrants, the other three quadrants, and we examined the species area relationships in those. And here they all fit the MaxEnt prediction rather well. This is actually not the best example or the worst. It was the intermediate of the three. And the MaxEnt prediction, the data for the non-barren quadrant, and just for fun again, other prediction, the Gleason prediction, and the Powerlaw fit. So it's no longer Powerlaw. The MaxEnt prediction fits it better, and we're saying to ourselves, well, what does this mean? It seems to mean that the theory doesn't work when you have some very distinct difference in the quality of the habitat in a portion of the plot. So we have to throw that away. I don't have it here, but if we just look at the species area relationship within that barren quadrant, it works quite well. But it doesn't work across all four. We asked ourselves, why is it Powerlaw-ish? More Powerlaw-ish for the Serpentine plot than for the tropical forest plots. And of course I mentioned earlier that the Serpentine plot was distinguished by a very small ratio of S0 to N0. So let's look numerically at what MaxEnt predicts for an ecosystem with 32,000 individuals as we vary the number of species. And both graphs are on the horizontal axis the number of species for this fixed number of individuals. So low S0 over N0 at this end, high S0 over N0 here. The Serpentine plot is about here. The tropical forest plots are in here. And what you get is that if we look at the R squared for a Powerlaw fit, it gets better and better and better as you approach a small value of S, which means a low value of S0 over N0, which means a small value for that Lagrange multiplier. And as the number of species increases, the R squared gets worse and worse. And I drew this line at around 0.99 to indicate where any reasonable person looking at the data would say there was curvature. If you're above this value of R squared, it's very hard to see curvature in the data. When you're below it, you begin to see it. And so the Serpentine data is right around that transition point. Here I'm showing the slope of the species area relationship if you fit the data to a Powerlaw. Now, you can fit any of these data with a Powerlaw. The fit is better and better out here. And here's what the slope of the species area relationship does. It comes down from 0.25, where it's not that great a fit, to a better and better fit, approaching a slope of 0.15. So a true Powerlaw SAR, we argue, will have a slope of around 0.15, and we're making the prediction that anybody who sees a really good Powerlaw in nature is probably going to see a value of around 0.15. So there, I've made the prediction that we were talking about earlier. Using MaxEnt, the ratios of these state variables determine the central tendencies of the empirical behaviors of the most widely studied scaling metrics in ecology. But what determines N naught, S naught, and E naught? Let's try to get more ambitious and ask, can we say anything about the state variables themselves? And now I'm going to get very speculative and turn to this third example, this third type of entropy law, the one I showed you at the beginning of the talk. We had classical second law, then we had the James max entropy principle, and number 3 was max entropy production. Let me explain it in the most famous context. The example worked out by Garth Paltridge, an Australian climatologist in the 70s. What he asked was, look, Navier-Stokes is hopeless. We're never going to understand turbulence from first principles. Let's see if we can't understand the most puzzling property of Earth's climate system, if you view it as sort of a, if thinking of us as just another planet. One of the things that's most interesting about us is that our equator is not as hot as it would be, and our pole not as cold as it would be if it were because of the turbulent transfer of heat from equator to pole, mediated by atmospheric and oceanic motion. So the equator heats up tremendously. It would be 30 degrees hotter than it is if it weren't for heat transport, and the pole would be about 30 degrees colder. So what determines the rate of energy flow from equator to pole? And Paltridge made the astoundingly bold assumption that entropy production is maximized. Let me explain how he did the calculations. Literally a back-of-the-envelope problem, and it's fun to work out. So let's set up the problem. We have omega E as the heat input from the sun at the equator, and omega P is the solar input at the pole. It's the net input, so it's the gross incoming energy minus the reflected energy from the albedo of the equator or the pole. And energy conservation at the equator says that omega E is going to be sigma T to the 4th, which is the radiant heat back to space from the equator, and 2Q, because Q goes both up and down. So that's very crudely. You can work this out in more complex format. You can have multiple latitudinal bands. You can make all kinds of complications, but this is the bare bones simple result, and you actually get the same answer you would if you did it more realistically. At the pole, we have omega P plus Q equals sigma TP to the 4th, the outgoing infrared from Stefan Boltzmann at the pole. The entropy flow is going to be the rate of heat flow, Q. I'm calling Q not heat, but heat flow. It's a flow rate, divided by the pole temperature minus the heat flow Q divided by the equatorial temperature. And that's equal to, using energy conservation, this expression. Now, max entropy production says maximize this by varying Q and see what Q you get. And whatever Q you get should be the Q nature picks, if the principle of maximum entropy production is valid. And you do it, and you find that as a function of Q, the SDT has a maximum. You work out what the maximum looks like. You can substitute that into here to get the temperatures. You get the right temperature at the equator. At the pole, you get the right heat flow. It works. And Paltridge published a series of articles about this, which everybody said, wow, that's astounding, and then kind of ignored. So the question is there anything to this, and why should we believe max entropy production? Well, anything to it. Interestingly, it also works for Mars and Titan. Should we believe it? Well, interestingly, in 2003, a physicist named Roderick Dewar proved from first principles, rigorous thermodynamic kind of proof, starting with the James max entropy principle, he was able to prove the maximum entropy production rule. Now, fairness in advertising, truth in advertising, his proof has come under some scrutiny, as of course it will, because it's almost Nobel Prize work, and it has been questioned, and somebody has said that there's a problem, and I have not been able to follow all the back and forth on this. I haven't had time, for one thing, but even if I did, I might not understand it. And the idea is that probably he's going to have to go back and patch it up or throw it out. We don't know. But it's interesting that it works. It may be interesting that it's rigorously proven. But the question now is, can we apply this principle to macroecology? And here's the really speculative step that I'm making. I don't know why that's there. It's not supposed to be a happy face. It's leftover from changing the slide. Let's apply max entropy production not to thermodynamic entropy, which is what Poltridge did, but to information entropy. Why not? So we'll take the information entropy function R and integrate it over E, sum it over N, and take its time derivative. And that gives us the rate of change of information entropy, and then we can maximize that and see what we get. Now, I have not finished working this all out, but here's how far I've gotten so far. You can take the time derivative of this. It's quite straightforward. You get a result that depends on the rates of changes of the state variables. And this term in brackets is multiplied by something 1 over beta, and beta is the log of 1 over lambda, the Lagrange multiplier. Turns out not to depend on the other Lagrange multiplier. So this function can now be maximized by assuming that terms like n and s naught depend on, their time derivatives depend on s naught and n naught themselves, and maximizing this should give equations for predictions for the rate of species diversification over time. So that's the next step, and we're in the middle of trying to solve that. It turns out to be a complicated calculation, but I think it's doable, and we'll see what happens.
So John, just to understand that, does it make sense when you're putting together R, I don't know how you came up with R, but when you're doing that derivation for R, does it make sense to think of epsilon and n as things that are changing?
Well, those are variables. It makes sense to think of S naught, N naught, E naught as changing, because in ecological succession, those are changing.
So I understand ecologically it makes sense, but when you're doing this maximum entropy,
yeah.
So you're putting together R, does it make sense at that point to think about those?
When we do the max entropy thing, I think of it as a slice in time. So picture a tube, which is the evolving or succeeding ecosystem. And at any moment in time, you know an S naught, N naught, E naught. So at that moment in time, we can maximize information entropy and get the species area law at that moment in time, everything at that moment in time.
So you're not thinking about this as being an equilibrium situation?
No, not at all. And so let's say a disturbance comes along and wipes out everything. We now have data from Mount St. Helens on every year the recovery of the plant community over time. That's going to be the first data set we're going to test this against. But it should predict what happens when you start with a few colonizers divided amongst a small number of species, and then more colonizers, and the small number of individuals grows to a bigger number. And the relationships among those changes should be predicted by this if MEP applies to ecology. Big if. We'll see. Now, the last slide, except for summary slide, this is our grand vision of a unified theory of ecology. MaxEnt plus knowledge of the state variables, which information about which may come from max entropy production, leads to all these things: energy abundance distributions, species level spatial distributions, Fisher log series, species area relationships, things I haven't shown you but which also pop out of the theory, and endemics area relationship, range area relationships, etc., etc. From MEP, we can get diversification rate. Mark Ritchie and I are working on getting food web structure out of MEP. Possibly it will provide a derivation of metabolic scaling, and since these plus that give Demuth, we would then pick that up as loose change. So these question mark lines are all agenda things to do. Speculative. The solid lines are all done. And we think that if we can push this agenda through, we will have a theory of ecology that doesn't always work. Where it doesn't work, something interesting is happening, like it's all rock and no plants. But the idea is to develop this to the point where we can, start accumulating the failures, because it's in the failures of the theory that we're going to learn about what matters in ecology, what mechanisms matter in ecology. So, thank you.